In this video, I'm going to show you how to draw and read direction fields, or slope fields, based on a differential equation. A differential equation is an equation that contains an unknown function and involves one or more of its derivatives. When we refer to the order of a differential equation, we are referring to the order of the highest derivative in the equation. So for example, we have y prime minus y equals e to the x. The highest derivative is y prime, which is the first derivative, so this is called the first order differential equation. In the second one, we have y double prime equals to cos x plus y prime. So the highest derivative is the y double prime, which is the second order. The solution of a differential equation is going to be a function. And when you are asked to solve a differential equation, you are expected to find all the possible solutions of the equation. Now, you've actually seen some differential equations already, and the simplest one is one with just y prime equal to x squared. So something like this, when we find the general solution, we would say that y is equal to x cubed over 3 plus c. All right, but what happens when it's not just simply y prime? Now, before we get into that, we're going to take a look at integral curves first. When you solve a differential equation without an initial condition, you will get a general solution. So for example, let's say I ask you to find the antiderivative of dy dx equal to x. We would say that y is equal to x squared over 2 plus c. Let's say c was 0. So if z is 0, I'm going to graph x squared over 2, and I would get a parabola that looks something like this. And you can plug in values for x and solve for y. And this would be c is equal to 0. But we can say that c is equal to 1, and we would get a graph that looks like this. And we can say that c is equal to 2, and we get a graph that looks like this, and so on. So the c gives us a vertical displacement of our parabola here. So we can also say equals -1 and get a graph that moves down like so. And we'll draw one more, c equals -2. Now, assigning these different values to c, we can see that we get different curves, and this is called a family of integral curves, which represents a solution of the differential equation. So notice that the solution is actually a whole bunch of different curves. Now, if we are given an initial condition, then only one of the integral curves is the solution. So if I ask you to highlight where y of 0 is equal to -1, that means that when x is 0, we get a y value of -1, which would then be this graph right here. So this brings us to direction fields or slope fields. So it is not necessary to integrate and assign values of c to draw the integral curves. If we interpret y prime as a slope of a tangent line, then the differential equation states that at each point x, y on an integral curve, the slope of the tangent line is equal to the value of f at that point. So what we're going to do is we're going to take the dy dx and say that's y prime, which actually represents our slope, and we're going to draw little lines to represent the slope on the graph. So let me show you an example. In this example, I want to graph the family of functions that solve the differential equation dy dx is equal to y. by calculating the slope of the tangent line at each grid point and then drawing a small line segment through each point. So recall that dy dx, that stands for our slope. And notice that our slope is equal to y. And notice it's only dependent on y, but not x. That's going to help us draw our graph. So let's start at 0, 0. So when x is 0 and y is 0, which is right here, y is 0, that means our slope is going to be 0. So we're going to draw a little horizontal line to show that the slope is 0. When x is negative 1, y is 0, which is this grid point here. Then we can see that y is still 0. When x is negative 2, y is 0, negative 3, 0. So you notice that all of these numbers here, these are all 0, which means that everything along the x-axis, no matter what the x value is, the y value is still 0. And that's because the slope is only dependent on y. Let's take a look at a different column. So here we have the grid point 1, 1. So at 1, 1, we can see that it doesn't matter what the x value is, but the y value is 1. So at the point x equals 1 and y equals 1, which is this one here, we're going to draw a little line with a slope of 1. And you can do this by imagining, and I'm going to draw this and then I'll erase it after, by imagining that there's a line like this with slope 1. So what we're going to do is we're going to draw a little line that goes through this gray line that I've drawn. I'm going to erase this first and then draw my little line. Okay, at x equals 2, which is this point here, and y equals 1, the slope is still 1. So again, I'm going to draw a little line that has the same slope as this first one here. At x equals 3, y is 1. So 3 at the point 3, 1. Again, we have the same slope of 1. And you notice that this is true of all the values where y equals 1 and x can be any number. So all of these x values here, doesn't matter what it is, y value is always going to be 1. And what I do is I always line it up using my ruler so that it lines up like this, so that when I draw my line, it will match this ruler line. Okay, so I'm going to erase that so we can see it without it. All right, so let's go to the next value. So when x is negative 3 to 3, I will always get a y value of 2. Okay, so no matter what, when y is 2, we have a slope of 2. So again, to do this, let's say we pick this point here. What I like to do is then match it up. That gives me a slope of 2, so I'm going to match it to this point here. So I want to draw a line that has this slope, which I've drawn in gray. So I'm going to erase this and then draw it in blue, because I want to just draw a short one. So again, use your ruler and line it up so that it matches this point here. And then all the points, no matter what the x value is, when y is 2, the slope equals 2 because it's only dependent on y. Okay, when x equals negative 3 to 3, y is always going to be 3. So I'm going to put 3 all the way down. And again, so at 0, 3, this should point here have a slope of 3. So that should match this gray line here. So notice it's getting steeper as I go higher up in my y values. So let me draw in this one. And then all the values here will also have the same slope. All right, so let's take a look at the negatives. So we have negative 1, and that should be the case. So all the y equals negative 1s, we're going to have a negative 1 slope, which looks something like this. Okay, so I'm going to erase this and draw it in blue now. Okay, when x equals 0 and -2, which is this point here, it has a slope of -2. So we're going to draw slopes this time that have a slope that looks like this. Okay, so again, I'm going to erase this and pretend my gray line is a ruler. I just can't show you a ruler on the screen here. And the last one, all the y values will be -3. And that's what my slope is. So y equals -3. So I'm going to now draw steeper slopes this time. So when you take a look, this graph, let me just draw kind of one. It looks something like this, which you've seen before. It looks very exponential. So the resulting picture, what we have here in the blue lines, is called a direction field or a slope field. For the differential equation, dy dx is equal to y, because it shows the direction or the slope of the integral curves at the grid points. And the more grid points that are used, the better the description of the integral curves. Now, we don't normally draw this red line that we have here, so I'm going to actually erase that. Okay. But we would only have what we have in the blue, and that would be what we call our direction field.